Welcome to MyProjectBazaar.com. Now we discuss about the product for low power memory resistor based 70 SRAM using multi-threshold CMOS technique. To benefit from speed and area improvements, it's useful to scale the minimum feature size of devices. As technology scale, proportion of leakage power in the total power budget is increased. The increment is more for static random access memories because they spend most of the time in ideal mode, in which there is just leakage power. SRAM continue to consume large part of power budget in VLSI system because of regular increases on the die cache memory. An effective solution to reduce the active and leakage power to reduce supply voltage to operation in subthreshold region. In subthreshold region, MOSFETs suffer from short channel problem. This is due to the weak channel control in these transistor is subthreshold, which is also to increase the sensitivity to process variation in these devices. To support the short channel effect and to reduce leakage power, several device solutions were studied, including fin-shaped field effect transistor and microelectronic mechanical systems. Because of the better control on the channel, that leads to supporting short channel effect, low leakage current on higher on current. FinFET devices are interesting on sub-nanometer technology node. However, new devices solutions address some challenges of traditional devices for subthreshold operation and in nanometer area, but they increases the overall price because they are not based on conventional bulk CMOS technology. In general, they require several additional steps in the manufacturing process, which leads to more sensitivity to process variations. Because of higher uncertainty in nanoscale process, in this paper we propose a new SRAM cell using the conventional bulk CMOS technology. Besides the reducing of leakage power, it improves the leads to stability and increase the wide writability of SRAM. The rest of the paper is organized as follows. In this paper, we present a new 8 transistor design for static random access memory cell that is based on the traditional silicon technology and reduce the leakage power considerably compared with the conventional design. Proposed design can be fully functional at smaller supply voltage over the conventional 6 transistor SRAM cell. To verify the proposed design, a 32 kp SRAM is designed and simulated 90 nanometer CMOS technology using the proposed 8 transistor and conventional 6 transistor SRAM cells. Operating at the VDD minimum, simulation show improve the 58% and the 67% for write and read power per operation, respectively. For our design to address the challenge of half selection during the write operation, design the proposed cell can be fin-shaped field effect transistors, show less sensitivity to variation and improve the power consumption level. Next we see the flow diagram for the product. First, the input data bits to be applied for the our single bit SRAM cell. We develop the array based SRAM cell, and to develop the 8x8 bit storage based array cell SRAM cell to be designed. Each SRAM cell to be consist of the sleep transistor, and to apply the threshold function for our each 6 transistor based SRAM cell, and to apply the bit and selection line input, and to store the any of the 1 and 0 bit to be selected the each and every single bit SRAM cell, and to control the write input content data. Then to passing the read path functions, the read path function to be selected by the selected bit address decoder architecture. We develop the decoding architecture for row and column selection control, and we develop the two address selection decoder and column selection decoder, and select the two selections and to set the bit for read bit sensing process. The read bit sensing process to activate the overall SRAM cell, and to analyze the each SRAM cell, and to select the address bit, and to effectively identify the selected address content bit. Then to content to be address selection process, and finally we get the output stored data bits, and to analyze the all the things, then to calculate the performance analysis. Finally, we develop the overall 8 cross 8-bit arrays SRAM cell to be used in the CMOS logic. The CMOS logic to be consist of the NMOS and PMOS combination to be present in overall CMOS logic, and we focus the overall array cell for read and writing purpose, and to select the address selection process also. We select the address conditions and to set the two set bits of the address row and column selection, and they set the bit and read all the things. Whatever the bit is not set, do not read the data bits, and the bit is to be set, they read the output data bits effectively. This is our the final flow diagram for the product. And finally we see the output for the product. This is our the final output design. This designs consist of the three-stage decoder architecture for row and column selection logic. The row and column selection logic mainly used to address of the decoding functions. The address of the decoding function to be selected by the read function control. Each transistor, sorry, each each bit storage based SRAM design consists of the sleep transistor using the threshold function and read control logic. The read control logic to be write the data bits and to be read the final output data bits. The read control to be selected by the any one of the stored data bits and to be controlled by the row and column selection control. The row and column to be selected equally and to set the read selection control, and the read selection control to be set to get the output for the required stored data bits for SRAM design. We developed the SRAM design logic is 4 cross 8 cross 8 based array cell storage type. A storage type to controlled by the each transistors using the CMOS transistor, and we designs the overall memory structure based logic for our required sleep transistor based threshold logic applied by the SRAM design. This is our the final design for the overall product. And to run this design and to run this design to generate the output data bits. And the output data bits, we select the address decoding function is 101 and 101. So we select the fifth data bits only. So with the data bits only we selected, and another data bits to be 0. This is the 0 voltage function, this is also 0 voltage, and this 0 voltage function, this is also 0 voltage. This is only the 5 volt for R5 output. So we select the only fifth SRAM designs only. So this SRAM to be stored in one data bits for our required output logic. So we get the output for only the R5 output for using the threshold based SRAM architecture design. This is our the final output for our overall product.